Good day, class. We'll be looking at the concept of hard and soft acids basics. The subtopics under this course are classification and meaning of HSAB, which is a hard and soft acid basics. Then principles of HSAB, characteristics and differences of HSAB, applications of HSAB, then questions, some likely questions that we can come across during the examination. Before I will start the explanation, I want us to remember the concept of acid and base, which I'm going to cite about four scholars that give the definition, their concept, their knowledge about acid and base. Then we have about Arrhenius theory, we have Bronsted and Lowry's theory, and also we have Lewis theory. All these theories, the one that's comprises the one of Arrhenius, Loris, and Bronsted are the one of Lewis. So Lewis acid is electron acceptor, while Lewis base are electron donor. So that's why it is well accepted majorly in in most of chemistry aspects. So Lewis acid and base is the one we are going to be used in hard and soft acid basics. Now, classification of Lewis acid and base. According to HSCB principle, the Lewis acid and bases can be further divided into hard or soft and borderline types. But in this concept, we are going to look at majorly on hard and soft acid basics. Borderline is in between the hard and soft. They are not as hard and they are not as soft. That is why we also have borderline types. So now, let's look at the characteristics or behavior of a hard and soft acid. Hard Lewis acid are characterized by small ionic radii, high positive charge, strongly suffected empty orbitals in the valency shell, and with high energy lumos, that is lowest or least unoccupied molecular orbital. Now, examples of add Lewis acids are hydrogen, lithium ion, nitrogen ion, potassium ion, beryllium ion, magnesium ion, calcium ion, and majorly all the main group elements in periodic table ions are hard Lewis acid. Now, let's look at the soft Lewis acid. These are characterized by large ionic radii, low positive charge, completely filled atomic orbitals, and with low energy LUMO. They are like opposite of hard has Lewis acid, the one of soft Lewis acid. Now the examples we have the gold ion, mercury ion, cesium, magnesium, stellium. All these one are examples of soft Lewis acid. What of base? The hard Lewis bases are characterized by small ionic radii, strong suffected, highly electronegative, weakly polarizable, and with high energy HOMOs, called highest energy molecular orbital. Examples of hard soft basics are water, hydroxyl ion, fluorine ion, chlorine ion, ammonia, carbonyl, functional group, and also uh, alcohol. Majorly, all these one are hard Lewis basics. Now let's look at the soft Lewis bases. They are characterized by large ionic radii, immediate electronegativity and negativity, highly polarizable, and with low energy HOMOs. Examples of this one are cyano ion, thiocyanato ion, iodine ion. So all these are examples of soft um, Lewis basics. Now, what is the principle of HSEB? The principle that guides HSEB, according to HSEB concepts, hard acid prefer to binding to the hard bases to give ionic complex, whereas the soft acid prefers binding to soft bases to give covalent complexes. Now, these terms can be classified under HSIP, called hard-soft interaction, hard soft interaction principle. Now, the relationship in hard soft, base and acid is that hard acid always interact with hard base, while soft acid always like to interact with soft base. Like only man would like to marry a only woman, an only woman would like to marry an only man. So that is a relationship here. Now, what now give rise to this principle, like analysis, explanation under this principle? The first thing is that the large electronegativity differences between the hard acid and hard bases give rise to strong ionic interaction. That is, when a hard acid and hard base interact, so it is normal, which is that guide the principles of HSCB. They are going to head up on ionic complex. That is, they are going to form ionic interaction. But when soft base and soft acid interact, they are going to form covalent interaction. So one of the things is that there are large electronegativity differences between the hard acid and hard bases makes this to happen. The next one is the electronegativities of soft acid and soft bases are almost same, proximate, and hence have less ionic interaction. That is why when soft acid and soft base react, they are going to form covalent interaction. Now, let's look at the concept under FMO that we call fragment of molecular orbital. This one majorly used when the electrophilic and electrophilic molecules want to react. So according to fragment molecular orbital analysis, the interaction between acid and bases are controlled by the relative energies of the participating frontier molecular orbital, which are HOMO and LUMO. This one is majorly useful under the concept of crystal field theory. Then another analysis under this is that the greater the energy gap between the HOMO and LUMO, harder is the space. That is, the energy between those highest molecular orbital theory and the least unoccupied molecular orbital theory, the energy gap between them, the harder is the species. Now let's look at the characteristics and differences in hard and soft acid basics. Hard acid, they have small ionic radius, have high positive charge, they have low electronegativity, and they have high energy lumo. Hard base, small radius, they have small radius, small high electronegative, they are very high in electronegative and also weak polarizability, and they have high energy homo. Let's look at the soft acid. Large ionic radius, low positive charge, intermediate electronegativity, and they have low energy lumo. What of soft base? Large radius, they have intermediate electronegativity, and they are highly polarizability and low energy homo. Now, application of HSCB, that is where to use it. This we have numerous application of HSCB. So we now classify their uses based on these four ways. The first one is we use it in hydrogen bonding. The strong hydrogen bond is possible in case of water, ammonia, and hydrogen fluoride. The reason being this, since the donor atom, which is donor atom is a base, Lewis base, which is fluorine, oxygen, and nitrogen, are hard Lewis bases, and their interaction with partially positive charge hydrogen, which is a hard acid. So in hydrogen bond, for us to have water, to have ammonia gas, to have hydrogen fluoride, what makes that interaction to be more fluent and okay in chemistry is because hydrogen is under hard acid, Lewis acid, and fluorine, oxygen, nitrogen, they are under hard Lewis base. So that interaction really pave way for the hydrogen bond interaction. That is why when we dissolve some molecules into water, those molecules able to dissolve completely or partially to interact with the hydrogen to form hydrogen bond. The reason for those things to dissolve and form the reaction is because of this HIB HSAB interaction or knowledge. So another use application is a linkage of abidentate ligand to metal atoms. um This thing, are going to get to understand this linkage of abidentate ligands to metal atoms by the time I drop the video on complex compound, or we say complex chemistry. We call some ligands abidentate ligands. Examples of abidentate ligand is thiocyanate. They always come with a symbol of XCN, or we say NCX. This abidentate ligand, they have two teeth to bind themselves with to the central melter. Now, let me try to explain this through this note. It is one of the important application of the HSAB principle. The XCN, like thiocyanate ligand, is an abidentate ligand and can be X bond, like that is, it can be sulfur bond to metal to the central metal and referred to as thiocyanate or thiocyanate, or can be N bond, which is nitrogen bond to the central metal, and it can refer to as TOCyanate. The choice among the sulfur bond or nitrogen bond is decided by the soft or hard acid base behavior. So S is a comparatively soft base than nitrogen atom. That is, sulfur is a soft base compared to nitrogen atom. Hence, soft metal ion are bound while hard metal ion are bond with nitrogen. That is, if you want to link the central metal, whether to if you want to decide for central metal to bind to sulfur or to nitrogen, what will give us the best way to determine this is this HSAB. In what way? If the central metal is a soft Lewis acid, then it's going to bond to sulfur because sulfur is a soft Lewis base. But if the central metal is a hard acid, then it's going to bond to nitrogen. That central the ligand is going to bond to nitrogen because nitrogen is a hard Lewis base. So this concept of HSAB really make this thing to be more easier for that. That's why I show some about three reactions after this explanation. You can go through it. You can see cyano bond through the sulfur atom soft base when bonded to platinum 2 ion, a soft acid. Then it bonds through nitrogen atom, a hard base, when linked to chromium 3, a hard acid. So this is the one of the examples. Then you can check the three where we have the iron and also chromium. Now let's look at the third uh, application. Application of HSAB to predict direction of inorganic reaction. You know, when you have a reactant site and you want to form the product in chemistry, you will react either the base with acid, then you get the product. Now, what makes those elements react with each other to form the product? It is through this HSAB concept that will make chemists to form those reactions. HSAB principle is used to predict the outcome of few of the reactions. We can predict whether a reaction proceeds to the right or left based on soft or hard acid base interaction. For instance, let's look at this just one. The reaction between arsenic trifluoride and phosphorus triiodide is possible and proceed to the right, since arsenic ion is softer than phosphorus ion, and iodine ion is a softer than fluorine ion. That is, as arsenic ion is a soft acid and phosphorus ion is a hard acid, while iodine is a soft base and fluorine is a hard Lewis base. So through that, the reaction will now give us, when in the reactant side we have arsenic trifluoride plus phosphorus triiodide. If you want to form the product, we are going to have arsenic triiodide plus phosphorus trifluoride. So this one gives us the best way to determine the reactant, the reactant, the product side. The continuation under the application: solubility in water. The compound formed due to soft and acid due to soft acid soft base combination is more covalent and less soluble in polar solvents like water. When you say a solvent is polar, any solvent that can possess the molecules that can possess positive and negative ion, that's one by polar. Water is polar in nature because hydrogen is positive ion, the oxygen there, the hydroxy there is a negative, the hydrogen is positive, so it is polar in nature. So for example, let's look at the silver iodide, AgI. AgI, which is silver iodide, is insoluble in water. That is, AgI doesn't dissolve in water, has it has covalent, because it has a covalent bond. It is covalent in nature, since it is the combination of the soft acid and the soft base. In the beginning we said when the soft acid and soft base react together, they are going to form a covalent reaction. Now, on the other hand, let's look at the lithium iodide. L- Lithium iodide is the result of the combination of lithium, which is hard acid, and iodine, a soft base. Thus, it is a polar covalent and thus soluble in water. So, lithium um iodide, it is soluble in water. So, the reason why it happens this way is because a polar dissolve polar, while non-polar dissolve non-polar. um Silver iodide, it is a non-polar reaction. If we are to say it's a polar, it has a covalent reaction, so it can dissolve in water. Why lithium iodide can dissolve in water? Because it is polar, it has ionic interaction. And if you look at water also, it has a what? Ionic interaction. It is polar in nature. So that is what caused that. For instance, if someone mistakenly take a poison that contain lead, because lead is very poisonous, if the person is quickly diagnosed and know that, okay, and they detect that, okay, this is uh, lead poison, the doctors will be looking for editor. Editor is a ethylene diamine tetraacetic acid. This ethylene diamine tetraacetic acid editor would dissolve, will be able to attract the sulfur content and the lead content in that person's abdomen, and the person can either vomit it or urinate it out or defecate it out through the physics. What give the knowledge of all this is because of this knowledge of HSAB. So that is what is happening here. If we are to dissolve silver chloride and silver iodide in the water, it won't dissolve because um, water is a polar compound or molecule. Why lithium iodide would dissolve in water? Because of that interaction between the polar solvent and non-polar solvents. So uh, you can ask question if you say that if you have any question regarding to this knowledge of hard, soft, base, acid, you can put that in the comments section. Then here are some questions that you can solve, likely questions that you can come across in your exam. Some of these questions are university questions that uh, some students have done some years ago. Now, notes, you can check the answer in the notes to solve the problem, and then you put those answers in the comment section. The first one is compare and construct soft acid and soft base. That is, you can even try it for hard and hard base as well. Say the similarity and say the differences of soft acid and soft bases. You can also try for hard acid and hard base. Then number two, state four applications of the concept of hard and soft acid base. Then the number three, state the reason why silver iodide is insoluble in water while lithium iodide does. So you can use this through the concept of a HSAB concept. So just thank you for watching. Help us do the following: subscribe to our channel, like, share, and comment. Success shall be yours.